This video will cover the selection of a pump and mechanical sealing system for improving reliability. The problem was posed by Eneos, a private chemical corporation.
There are 3 deliverables required to complete the project. The first deliverable is to specify a new pumping system capable of replacing their outdated and leak-prone Sunflow P1000 pumps. The second deliverable is to specify a new mechanical sealing system that is better suited for their current Sunflow P1000 pumps. And then lastly, the third deliverable is to design a program that can estimate the amount of process loss in the event of a worst-case mechanical seal failure. The design methodology for the first deliverable starts with the main approach: source a pumping technology that eliminates or minimizes the cause of failure while meeting the process requirements. 3 pumping technologies were considered: the magnetic drive pump, the updated centrifugal pump design, the positive displacement pump. To the right, you can see the comments for each pump.
The final pump selected for the first deliverable was a Milton Roy Prime Royal positive displacement pump. This pump meets all the process conditions, has an explosion-proof motor, which is necessary since Eneos is working with hydrocarbons. It's compatible with the plant standard VFD that Eneos uses, and it comes with a 5-gallon pulsation dampener.
Few designs were considered for the mechanical seal system. The first one was to redesign the seal. This meant separating the tandem seals in order to isolate the seals from each other in case one of them failed. However, spacing inside of the pump did not allow for this design. The second one was IPI Plan 54, which kept the current seal, but introduced a pressurized liquid as the barrier fluid in the seal. It met all the process conditions. However, the barrier fluid could leak into the process fluid, thus contaminating it. The third one was an API Plan 74, which is extremely similar to the Plan 54. However, instead of a liquid, it used a pressurized gas as the barrier fluid, and it had a higher cost to pressurize nitrogen up to 275 psig. The final design was an API Plan 54. This kept the current seal, and as seen in the diagram below, it introduced a lubricator system to pressurize the barrier fluid and send it through the mechanical seal, and it was cost effective compared to the Plan 74. The lubricator used oil or ethylene glycol as the barrier fluid. It uses the pump to pressurize the barrier fluid from 100 to 1000 psig, and the standard flow rate is 1.5 GPM. However, the actual flow will be specified by John Crane engineers once they calculate what it is needed to have an adequate heat absorption. The cooling system will use water as the cooling fluid. Here is the engineering drawings for the lubricator system. As you can see, there is a vertical mounted motor that will power a pump below it, and under there's also some coils. There is gauges that will measure the pressure and temperature of the barrier fluid.
The third deliverable is an Excel-based process loss system that quantifies the amount of fluid that escapes the pump via a faulty mechanical seal. The system models the behavior of a fluid mixture containing isobutane, propylene, and/or ethylene at a range of temperatures and pressures. A picture of the calculator can be seen on the right of the screen. The colored cells at the top are locations for user input that define the type of fluid flowing, as well as the pump dimensions. Below this area is the equation derived in order to solve for the mass of the lost fluid. Some assumptions that are key to this equation being valid are that there's laminar, linear, constant velocity, and steady state flow of the fluid, and a constant flow area through the mechanical seal. The calculator then displays at the bottom the rate at which fluid is leaking to the atmosphere on a mass basis.
Moving on to the lifecycle cost analysis, we'll take a look at the inputs for the existing system. Many of the costs generated by this system have to do with the replacement cost for the mechanical seals. Here we can look at the new pump system, which has to do with the new pump and the lubricator. All of the yellow values are known and the orange values are assumed. In this slide, we can compare the two systems with the costs affiliated with the new pump in red on the right and the costs affiliated with the existing system in blue. As you can see, it'll take about 6.5 to 7 years for the cost of the new system to be more beneficial than the cost of the existing system.